All right, number 24. Oh, let's look at 29. All right, number 24. What fuel flow should a pilot expect at 11,000 feet on a standard day with a 65% maximum continuous power? So we're looking at a standard day. So we'll be looking at this particular column. However, we do, all right, so at 11,000 feet. So 11,000 feet is between, well, obviously it's between, but it's between, between here more or less, all right? So that's where the orange line indicates is what 11,000 is, all right? Next. What fuel flow should a pilot expect at 11,000 feet on center day with a 65% maximum continuous power? So let's look at the theory. Note the entire chart applies to 65% maximum continuous power. All right, so so use the middle section of the chart, which we know, which is labeled a standard day. The fuel flow at 11,000 feet on standard day would be 1/2 of the way between the fuel flow of 10,000 feet and 12,000 feet. Yes, which is what I've indicated. So the fuel flow for 10,000 feet is 11.5. And the fuel flow for 12,000 feet is 10.9. And the fuel flow is here. Oops. Is here. So the fuel flow that we see is these two numbers. So once again, we have to find the mean to get 11,000. That's all. So let's add them, 11.5 and 10.9. When we add these two together, we get 20.4, and we divide that by 2, and we get 11.2. And 11.2 is our answer for number 24. All right, so let's go on to number 25. Number 25. What is the expected fuel consumption for a 1,000 nautical mile flight under the following conditions? And it provides the following conditions. So when we're trying to find the knots, you basically keep in mind, all you have to do is the whatever the nautical miles is over the knots, okay, and then you're going to times that by the GPH, right, or the fuel flow GPH. And if you keep that in mind, the problem is not so difficult. All right, so whatever the nautical mile is. Actually, I should erase that X. But anyway, more or less. Now back to the problem. So we have 1,000 nautical miles. And the knots that we are provided, let's see here. Well, we have to look for it. So the pressure also, let's see here. Let's look to our chart for assistance. So we need to find the knots from which column. So it's neither this nor this. It's going to be this one probably, most likely, especially with the temperature being a 22, right? Which is given in 20.8. So all this information, oh my, all this information is here in this column, right? 22, the temperature and the manifold of 20.8. So it's within this certain block. And the knots is this column. So for 22, the knots is 164. All right. So we have this times the GPH, right? The fuel flow. And this is 11.5. And then if you were to do the math, we have 1000 divided by 164, and we get about 6.09. We multiply that by 11.5, and we get roughly 70.1, and that is the answer for letter B for number 25. All right, that concludes that. The next problem, number 26, is similar. So we have what is the expected fuel consumption. Once again, we're looking for the fuel consumption for 500 nautical miles flight under the following conditions. So we'll, as I said, it's nautical miles over knots times your GPH. Right? So our nautical miles on this one is 500, excuse me. The knots, so we have to find out. So the numbers are 29 temperature and 21.3 manifold pressure. So let's look at the chart to find out where that will be. That is the last chart. This one. The numbers are here. 29, 21.3. All right, and our knots is 159. Right there. 159. And we're going to multiply by our GPH of 11.5. And that should give us our answer. So this one I have to work out. 500 divided by 159 equals 3.14 times 11.5. And that gives us 36.16. That is close to letter B. All right, that concludes that. Let's move on to the next problem. Number 27. Number 27, 28, and 29 are identical in the format of what's transpiring. So determine the approximate manifold pressure. So now we're trying to find the manifold pressure. All right, setting with 2,450 RPMs to achieve 65% maximum continuous power at 6,500 feet with the temperature of 36 Fahrenheit, higher than standard. So let's look to see how we can solve this particular problem. So the data is all on there. So what we see here is, let's look at the first part. We're using all, in this particular problems, 27, 28, 29, we're using all the whole table. These tables are confusing sometimes. Sometimes using a part of them, two of them, three of them, the whole of them. It's interesting and This is not something I think we're used to even in high school. All right. So the first number I see here is 6,500. So that tells me that I'll be looking between these two numbers, or what I'll go ahead and do is since 6,500 is not too far off from 6,000, I think we can use that. Well, I'll just separate this particular row is what we'll be looking at. All right. Next thing is, let's see here what we're looking for. And it says with a temperature of 36 Fahrenheit or higher. 36 Fahrenheit or higher would be this column or this particular box. All right, now let's move on. Now it's asking us, determine the approximate manifold pressure. So the manifold pressure, now for a different color, is this box, right? So what is in this box within this column? So what intersects is this, right? Or specifically this, what I just highlighted, which is 21.0. And that is the answer. So the same procedure or style of thinking for 28. So 28 is approximately what, excuse me, what true airspeed should a pilot expect with 65% maximum continuous power? That's the name of the title, 65% maximum continuous power at 9,500 feet. So at 9,500 feet. So let's look for this 9,500 feet. There is no specifically, specifically that's not there, but 10,000 is. So we can use the 10,000 section. We can use the 10,000 section. Now looking at that, next thing it says, same thing, 30 with a temperature of 36 Fahrenheit below our standard. So we're looking at this column, and we're trying to find we're trying to find what exactly? The MPH, right? So looking at that, it would be this 184. But because we're looking at 9,500 feet, which is less than 10,000, it's definitely going to be less than that. So between 181 and 184. And the answer is, oh, look right there, we have C183. Great. Next number, 29. 10,500. 10,500. We're kind of close to 10,000, right? So we can use the 10,000 section again. Let's see what else it says. With a temperature of 36 Fahrenheit above. So we're using this column. All right. What true airspeed should, so how many knots? All right, so let's look for the knots, KTS. So what we have here is 166. We're looking for above 166, or near 166. So 165 is the closest, so that's the answer, which is C. And that concludes this section.